Okay, now that we know the molar volume of a gas, let's see about some applications of that information. Okay, so just remember, at standard temperature and pressure, the volume of 1 mole of a substance is 22.4 liters. Okay, so technically this is most true at standard temperature and pressure, but it's for our purposes, we'll just use this regardless of the temperature. Okay, so every kind of gas has this exact same molar volume. So mass or size of the element doesn't change the volume here, and that's because it's a gas. It's not restricted by the size of the individual particles. What it's restricted by is the space it can take up. Okay, and gases can move about and take up the same amount of space regardless of their molecular size. So, your key relationships around the mole. What I like to call this is mole island, okay? Because everything focuses around the mole. Mole island. If you know moles of something, from there you can figure out the liters of a gas. You can figure out how many atoms or molecules you have, or you can figure out the mass of it using molar mass. Okay? So all of this can be done through dimensional analysis, knowing that 1 mole is equal to all of these things in the center, or like in between the places. Okay, so if you need to go from moles to grams, you use your molar mass and 1 mole in dimensional analysis. If you're going from liters to moles, you use the molar volume in 1 mole. Okay, or if another thing this visualizes is there any direct connection between, say, grams and liters, or grams and atoms? You should be saying no. If you need to convert from, say, grams of something to grams of hydrogen gas to volume of hydrogen gas, you will first have to convert to moles. Okay, something else to keep in mind is the process to get off of mole island versus onto mole island. There is a pattern to it. If you think about setting up your dimensional analysis to go 2 liters, okay, so you're in moles, so it's moles on the outside, you put moles, 1 mole in the bottom, and 22.4 liters on top, you multiply. To get back onto mole island, going the other way from liters, you're going to put your 22.4 liters on the bottom, 1 mole on the top, you divide. Okay? This pattern holds true for all of the other directions too. If you're going from mole to atoms or molecules, 1 mole goes on the bottom, Avogadro's number goes up top. Okay? And likewise, if you're going the other direction, it's going to be 1 mole on top and Avogadro's number on the bottom. And the pattern holds true for your molar mass as well. Okay? I always set up the dimensional analysis because that makes it's easy for me to remember to cancel out my units. But you can sit there and memorize that to get off of mole island, you multiply, and to get onto mole island, you divide. Okay? So, now that we know about molar volume, there is an extension to Dalton's law of partial pressures. So far we dealt with, if you're given pressures or given percentages, you can use that to find the individual pieces. But because molar volume is the same regardless of the kind of gas, that you can use the moles of gas in order to actually help you find percentages. So what that looks like. Okay, so if you know your number of moles of each gas, you can find the percentage of your individual gases and then multiply that by your total pressure. So you actually might be able to have less information and still be able to find out some more. So what that looks like is your P pressure of X. Okay, X is the gas in question, what you want to find out. Okay, P total is still your total pressure. The lowercase n stands for mole. Okay, So to find the percentage of gas X, you need to know the moles of gas X and your total moles. And that gives you your percentage. Okay, so NX is moles of the gas in question. And then N total is total moles of all gases. Okay, so let's see a problem like this. So U of the gas is measured at 45.8 pounds per inches squared. The gas is made up of 4.0 moles of oxygen and 32 liters of nitrogen. What is the partial pressure of the nitrogen gas? So I don't have any information about the pressures of my two gases, but I do have enough information to know the moles of both. Okay, one, oxygen's given to me. I know I have 4 moles of oxygen, but nitrogen I am given a volume, which I now know how to convert to moles. So if it's 32 liters of nitrogen, there's 22.4 liters of nitrogen in 1 mole. Nitrogen would be diatomic. Nitrogen, again, doesn't matter. Diatomic only affects your molar mass. And that ends up giving me, when I round 4 sig figs, 1.4 moles of nitrogen gas. Okay, which means now I know how many moles of nitrogen gas I have. I know how many moles of oxygen gas I have. I can combine those to get my total. So 1.4 plus 4 equals a 5.4 mole total. And then to figure out my percentage of nitrogen gas, I would do, so here's where I'm doing this. The px equals pt nx over nt. Okay, so my total pressure is 45.8. I'm going to multiply that by the 1.4 moles over 5.4 moles. What ends up being kind of like 45.8 times almost 26%. Or that gets me a number like 11.9, but ultimately my 32 liters with 2 sig figs controlled everything, so I have to round that to 12 pounds per inches squared. Okay. Another thing that you can do knowing molar volume is stoichiometry with gases. Okay. So just keep in mind the entire point of stoichiometry is so that if you know information about one product or reactant, okay, something you can convert to moles. So you might know how many molecules you have, you might know the mass you have, you might know the volume you have, okay? You're going to convert that to moles, apply molar ratio from the balanced equation, and then convert it to whatever units you need your final answer in. Okay, for the most part, there are 3 steps to stoichiometry. First step is you convert to moles. You're going to be using something off of that mole island. Okay, the most important step is the molar ratio step. It's the one that's the easiest to leave off, but that's the most vital part because that's what makes sure that you are using things in the right quantity according to your balanced equation. Okay. So if you think about substance A being here and we're trying to get to substance B, it's always going to be blank moles of A on the bottom so that you cancel that out and you're converting it to blank moles of B. And what goes in the blanks, these numbers here, those come from your balanced equation. Okay? The most common mistake I see is leaving that step off. And then the last thing is you convert to the units the question is asking for. Again, this is going to involve that mole island. If you need to know volume, you use the 22.4 liters. If you need to know mass, you use your molar mass. If you need to know how many molecules. If for some reason you only need to know moles, then you don't even need that step. Okay? So the key with stoichiometry is pay attention to your units. Those tell you what to do. Okay? And I honestly think you should write out units of what, so that you don't forget about this step here where you have to change from units of chemical A to units of chemical B. Okay? So, a couple of sample problems with that. If you react 0.567 grams of aluminum with hydrochloric acid, what volume of hydrogen gas would you expect to make? So I've got aluminum plus hydrochloric acid is going to make aluminum chloride. Here I need to think about my ionic bonding rules. Aluminum is 3 plus, chlorine is 1 minus, so that means I'm going to need 3 chlorines to cancel out the aluminum's charge. And then hydrogen gas, gotta remember that is diatomic. If you leave that 2 off, it totally screws up your balancing. So now to balance, I could start out by putting a 3 here, but then I'm going to end up with an odd number of hydrogens and I have an H2 on the other side. So what that means is I'm actually going to end up having to double everything. So I'm going to switch this out for a 6 so that I can put a 3 here, and that balances my hydrogens. Okay. Now to get 6 chlorines, I'm going to have to double my aluminum chloride, which means on the front side I have to double my aluminum. So now that I have my balanced equation, let's set up my stoichiometry. So I'm starting in grams, which means I need to convert from grams to moles. So I'm going to use my molar mass. 0.567 grams of aluminum. And aluminum has a molar mass of 26.982 grams of aluminum, and that's going to be equal to 1 mole of aluminum. Okay. You could sit there and calculate the number here, but when it comes down to sig figs, you really don't want to round until the very end. So I set up the rest of my multiplication steps. Now that I have canceled out my grams of aluminum, and I'm in moles of aluminum, I can apply my molar ratio. So from my equation, it's 2 moles of aluminum. And then I want to know about hydrogen gas. 2 moles of aluminum are used for every 3 moles of hydrogen gas made. Okay? And then last step, now that I have canceled out my moles of aluminum, I'm in moles of hydrogen, I need to convert those moles of hydrogen to what the question's asking me for. And the question's asking me for volume. Okay, so I know 1 mole of hydrogen is equal to 22.4 liters of hydrogen. Okay. That's going to take me from moles of hydrogen to liters of hydrogen, which that's the unit I want to answer the question. So now I do my calculations. Everything on top gets multiplied, and everything on the bottom gets divided, which in the end gives me 0.7060 and some more numbers, okay, which to make a judgment call on sig figs, I started out with 3, so I actually can't keep that 0 to get rid of it. But the 6 remains the same because I didn't need to round that up, and my units will be liters of hydrogen. So, one more example. This one, the equation's given to me, but always double check and see if those are balanced. So I have 3 oxygens and 1 nitrogen in the beginning, and then I need 2 and 4. So I need to throw a 2 out front here to balance that. And then if 0.76 liters of dinitrogen tetroxide was made from the above reaction, what volume of nitrogen monoxide is required? All right, so the only thing I have information about is the dinitrogen tetroxide. I know how many liters it is. Point of stoichiometry, I have to get things to moles. So 0.76 liters N2O4. There are 22.4 liters of dinitrogen tetroxide in every mole of N2O4. Alright, so I've gone from liters of N2O4 to moles of N2O4, which means now I'm ready for my molar ratio. which coefficient, there is no number written, which means my coefficient for N2O4 is 1 mole N2O4. And I'm going to the nitrogen monoxide, so I need 2 moles. I need 2 moles of NO for every mole of N2O4 made. That gets me from moles of N2O4 to moles of NO. Alright, so now I'm at the chemical the question's asking me about. So the last step, I need to convert it to the unit that the question is asking for. And I want to know volume. So I know 1 mole NO is equal to 22.4 liters NO. Okay. So that gets me from moles of NO to liters of NO. So if I do my math, I multiply everything on the top and divide by everything on the bottom. I get, it ends up giving me 1.5, I think it's 52 liters. But if I think about sig figs, that 2 is an extra significant digit. It won't affect me as far as rounding, so I have to remove that one. So my answer would be 1.52 liters of NO. Okay. So if you're struggling with stoichiometry, come in and get help. But make sure you do the online quiz, and I'll see you in class.